Hello, welcome back to General Chemistry 1. My name is Daniel, and in this video we're going to be looking at what's called intermolecular forces. So, in the previous few videos we've been looking at the bonding between atoms within a molecule. And that's what's known as an intramolecular force. That's the forces that occur in between atoms within one molecule. However, an intermolecular force is the attractive and repulsive forces that occur in between separate, different molecules. So if we have two molecules of something, for example, there's going to be different forces that are at play between those two molecules. And these intermolecular forces lead to certain characteristics of each compound when it's in its pure state, as well as when it's in a solution. So we're going to first start off by just looking at all the different types of intermolecular forces that we can encounter. And then later we're going to get into how strong they are, as well as some of the effects that occurred based on intermolecular forces. So let's start off with just looking at the different types of intermolecular forces. We have ion-based ones up here. We have dipole-based ones. And then finally we have what's called London dispersion forces. And we'll get into each of those set one by one now. So first one we're going to look at is ion-ion interactions. And you should be familiar with this from when we talked about binary salts. So when we have a compound that forms ions in solution, there's going to be an attraction between the positive cation and the negative anion based on Coulomb's law. Coulomb's law just describes mathematically the attraction between oppositely charged ions. So that's going to be largely based on the distance between them, and more important for us is the magnitude of their charge. So let's say we have a +1 cation here, a -1 anion here. There's going to be attraction, an intermolecular force between the two ions that's based on Coulomb's law. Where intermolecular forces come in is that if we have another one, let's say we have another positive cation down here, there's also going to be attractions like this and like this in between them. So what happens, as we'll see in Gen Chem 2 more, with ions is that they'll form these things called crystal lattices, all of these different anions and cations sorted together within a macromolecular crystal structure. But we'll save that for Gen Chem 2 for now. What's important here to note is that since Coulomb's law is based on the magnitude of charges, the greater the charges on your ions, the greater ion-ion interactions play. So for example, if we had a +2 and a -2, that's going to be stronger than something with just +1 and -1, just because of these Q's here on Coulomb's law. Okay, so we're only going to see these really in our different salts. That's going to be things like NaCl, FeO3, just anything bonded with a metal bonded to a nonmetal that forms ions in a solution or in its solid compound. So the next one we'll look at is what's called ion dipole forces. Now this one is known as a mixture intermolecular force because it involves two different compounds when they're mixed together. So an ion dipole force involves an ionic compound and then a molecule with a dipole moment, which is also, as we know, a polar molecule. So we have an ionic compound mixed with a polar molecule. And what happens there, if you look at the picture, is, okay, we formed our ions. We have our negative anion on the left, our positive cation on the right. And what will happen is that the polar molecule will align itself with its partial negative, partial positive charges to be aligned with the opposite charge. So for example, we see that the partial positive charge here is next to the negative anion. The partial negative charge here is next to the cation. And there's an intermolecular force that occurs between the ions and the partial positive, partial negative charges that are a result of the dipole in the polar molecule. So, like I said, this is only going to happen when we have a salt or something like that dissolved in a polar molecule. That most common example of that would be something like just a salt dissolved in water. So water is going to align itself so as to maximize the interactions between itself and the ions that are dissolved in it, as we saw here with the alignments of partial positive, partial negative charges. So those are our ion-based forces that involve ions in a solution or in a compound. The next one we're going to get into is dipole-based forces. So first one we have is the most simple. The dipole-dipole force is going to occur between two polar molecules. And let's look at how that happens. So as we know, any polar molecule is going to have partial positive, partial negative sides. We see that drawn down here like so. So what will happen then is, since we have a partial negative here and a partial positive here, there's going to be an attractive interaction between these two, like so. So the two separate molecules we have pictured here are going to align themselves based on having partial positive charges next to partial negative charges to form a dipole-dipole intermolecular force. The entire reason why they're attracted to one another is because they have partial positive, partial negative charges. And as we said, this is going to occur with polar compounds only. Or it would also work in a mixture of two polar compounds. For example, ethanol in water would be an example of a dipole-dipole force as well. Then the final thing to talk about is the relative strength of dipole-dipole forces. So if we have a stronger dipole moment, meaning that there's a greater electronegativity difference between the two atoms in the bond that we're talking about, that's going to make a more positive or more negative partial positive or partial negative charge, meaning there's going to be a greater concentration of charge on each side of the molecule. So if we had something like HF, that's going to have larger dipole moment than something like, HC, because F has more electronegativity than C, and hence there's going to be a stronger dipole moment in HF. And what that means then is that's also going to have stronger intermolecular forces in between two molecules of HF compared to two molecules of HC, because there's a greater dipole present in HF. So that's dipole-dipole forces. Next one we have is on a similar fashion, we have what's called hydrogen bonding. So hydrogen is a special atom because it's so small, and that means that other atoms can get very close to hydrogen because of its very small size. So hydrogen bonding is a dipole-dipole force, but it's a special dipole-dipole force, particularly a stronger dipole force. And it only occurs when you have atoms of hydrogen and they're bonded to nitrogen, oxygen, or fluorine. These are highly electronegative atoms. So it's going to be the same kind of thing as dipole-dipole forces. All of these partial positively charged hydrogens in water, for example, are going to align themselves with the partial negative oxygens. And we're going to have these kinds of interactions, attractive intermolecular forces in between all the different hydrogens and the oxygens. And it's going to form this kind of intermolecular force network within water, which is one of the reasons why water has such its special properties, as we've seen in previous videos. Okay, so biggest thing here is that hydrogen bonding is just a stronger form of dipole-dipole forces, and it's going to occur in molecules that contain hydrogen alongside nitrogen, oxygen, and fluorine. Okay, so next one we can look at then is what's called dipole-induced dipole forces. This is another kind of a mixture-based force. So this is going to be a mixture of polar compound and nonpolar compound. One example of that would be a noble gas such as argon dissolved in some kind of polar solvent, in this case HCl. So typically argon's not going to have a dipole moment because it's a nonpolar molecule. What can happen, however, is as this HCl with its partial positive, partial negative sides approaches argon, it can induce a dipole in argon. So for example, if this starts moving towards argon, all the electrons that are evenly spread out inside of argon's orbitals can be kind of pushed away from the partial negative charge. And that's because, unlike like charges repel one another, and so the partial negative side of this HCl is going to repel the negative electrons within argon. And this is going to induce a temporary dipole. If all the electrons move this way, it's going to leave a partial positive charge on the left side and make the right side more negative.